Hello, I'm Sahar Karufa from Ajman University. We have known for a long time that human activity in urban settlements generates heat. This is more true in modern times where we have skyscrapers, roads, industry, cooking, air conditioning, all of these add to the problem. And it is especially true in the hot areas of the MENA region where the UAE resides. Now, we are going to try and shed some light on this issue by comparing neighborhoods from different densities, zones, and forms. I now leave you with my co-author, Mrs. Ayat Al-Khazindar. Thank you.
Hello, everyone, and thank you for attending this presentation. I wish I could be there with you today. I am Ayat Al Khazindar from Ajman University. This conference is an important one because it deals with the rapid urban cities design, planning, and construction. With the recent rapid urban growth and expansion in the UAE, the urban heat island becomes one of the main problems which are facing the users, as it has a significant impact on human thermal comfort, health, and environment. In addition to that, it has an indirect impact on energy consumption and the high cost for cooling and heating the buildings. That's what this presentation is about, specifically about the effect of the different urban forms and densities on the temperature variations during the year. First, a brief introduction to the urban heat island. Recently, the urban heat island phenomena considered being one of the main problems that facing human beings, which is associated with urban growth and expansions in the cities. That's why most of the researchers focus on the urban heat island topic and the temperature variations due to several factors. Let us begin by defining the main terms in this presentation. The basic definition of the urban heat island phenomena is a metropolitan or urban area that significantly has a higher temperature than rural areas and surroundings because of human activities. While the urban form represents the physical characteristics of the city, it refers to its shape, size, settlement configuration for a specific area or the whole city. The urban form features vary from micro and macro scale. It could represent building facade and materials, while on the macro scale can refer to the urban form, building form, and street geometry. Urban density is considered to be one of the non-physical features of the urban form. There are several factors of the urban heat island phenomena and density as illustrated. The usage of the low albedo materials, lack of vegetation and trees, the existence of the high-rise buildings close to each other will trap the heat, which will cause the urban canopy layer. In addition to that, the heat is trapped in the dense urban areas due to the reduction in the wind velocity, which refers to the wind blocking. Chi-Ani has identified some factors that affect the intensity and the occurrence of the urban heat island. These factors are categorized into two extensive categories. First, the urban parameters, second is the meteorological factors. The urban parameters can refer to the city size, location of the city, urban geometry, land uses, built up areas, and density, while the meteorological factors would refer to humidity, cloud cover, and wind direction and speed. There are many effective mitigation processes and strategies to mitigate the urban heat island intensity, as using green roofs, high albedo materials and pavements, green vegetation, using shade trees and water bodies. In this research, the impact of the urban design and planning process on the urban heat island was investigated as shown in the figure. The proper urban planning of the city will have a crucial role in the urban heat island mitigation, as utilizing the wind paths and corridors to be oriented towards the prevailing wind in order to cool down the microclimate, modification in the building form to suit the climatic conditions, and the urban layout with the maximum shaded areas. Study investigated a large area of the city with its streets and the whole context rather than the relationship between two buildings form, since urban heat island is affected by urban geometry. Our methodology was based on selection of three traditional old sites with different densities and on the other hand three modern sites with different densities with a fixed area of 200 by 200 meter. then analyzing the urban configuration characteristics of each site as the orientation, the building form, height to width ratio, street geometry, and the sky view factor. The six selected sites were modeled and simulated through the NVMet software in summer, winter, and spring. The data were extracted and the results were analyzed to identify the optimum urban form that reduces the urban heat island impact and achieve the more thermal comfort for the UAE weather. The six sites are divided into two groups that are following two main approaches with different densities, the old traditional configurations and the new modern configurations. The first site is Al Marija Heritage Area in Sharjah. The location and the general urban form and layout are illustrated in these images. Al Marija area represents the old low-density traditional urban case that has courtyard urban clusters with narrow alleyways and zigzag road networks ranging from 2 to 3 meter wide. The building blocks are low-rise, represents 1 to 2 floors. The second site is Sidro area in Ras Al Khaimah. The location and the general urban form and layout are illustrated in these images as well. The Sidro area represents the old low medium density and traditional urban form, has compact urban clusters with narrow alleyways ranging from 2 to 3 meter wide. The building blocks are low rise with 1 story height. The third site is Al Fahidi Heritage Area in Dubai. Al Fahidi area represents the old high density and traditional urban form that has very dense and compact urban clusters with narrow alleyways ranging from 2 to 3 meter wide. The building blocks are all low and mid-rise, ranging between 2 to 5 story height. The modern sites, the first site is Al Mamzar area in Dubai. Al Mamzar area represents the low density grid urban form which has detached low rise villas with 1 to 2 story height that typically are placed in the middle of their plots. It has a gridded wide street system at 6 meter wide. The second site is Jumeirah district in Dubai. The location and the general urban form and layout are illustrated in these images. Jumeirah district represents the old low medium density, which has detached low rise villas with 1 to 2 story height. It has a gridded wide street system at 6 meter wide. The third site is Al Safa area in Dubai. Al Safa 1 district represents the high density modern grid urban form, which has attached low rise villas with 2 story height and gridded wide street system are ranging from 6 to 8 meter wide. It's significant to identify the constant factors that are fixed in the simulations. The independent factors will be investigated and examined in the dependent factors, which are changeable based on the changing of the independent factors. The constant factors were the building materials, the day timings, the climatic data, as the air temperature, wind speed, and direction based on the desired season, while the independent factors were the urban form orientation, building form, street geometry, walkways, and urban density, while the dependent factors were the air temperature, wind speed and direction, humidity levels, and mean radiant temperature. And kindly note that the vegetation and the water bodies were excluded in all the simulations. Simulation duration was 24 hours and the simulated days was 15th of August, 21st of December, and 15th of April. There were two main limitations while working on the NVMet simulations. First, the software workspace has a limited number of grids that represents a small part of the urban districts in reality. Therefore, the used grid ratio will be 1 to 2. That means each grid point in the workspace will represent 2 meter in reality. Second, there were difficulty in drawing many different angles, tilted and diagonal edges in the NVMet software. Hence, the model's orientation was corrected to have most of its lines parallel to the workspace to avoid the diagonal lines, while the remaining tilted facades have been treated as a staggered wall to get the correct angles. In order to ensure that the selected sites have different urban densities and to evaluate and assess them based on fixed criteria, the size of the urban plots was unified to all sites as 200 by 200 meter, which equals to 40,000 square meter. Starting with the old sites, the first model represents the real configuration of Al Marija area in Sharjah, which is low density with a total built-up area of 14,000 square meter, while the second model represents the real configuration of Sidro area in Ras Al Khaimah, which is low to medium density with a total built-up area of 17,500 square meter. The third model represents the configuration of Al Fahidi area in Dubai, which is high density with a total built-up area of 67 square meter. The height to width ratio and the sky view factor were calculated and showed that the high density area recorded the highest height to width ratio and the lowest sky view factor. The street orientation was analyzed for each site as well. It was noted that in the first model, which is Al Marija area, the urban canyons are in the same direction of the prevailing wind, which is the northwest. Regarding the new sites, the fourth model represents the real configuration of Al Mamzar area in Dubai, which has detached modern and low density urban form with a total built up area of 7,200 square meter, while the fifth model represents the configuration of Jumeirah district in Dubai, which has detached modern low to medium density urban form with a total built up area of 10,000 square meter. The last model represents the real configuration of Al Safa area in Dubai, which has attached modern and high density urban form with a total built up area of 39,500 square meter. The height to width ratio and the sky view factor were calculated and showed that the high density area recorded the highest height width ratio and the lowest sky view factor. The street orientation was analyzed for each site as well. Based on the 18 simulations were run in conducting this research, the main findings can be concluded based on three main aspects. First, the urban form. Second, the urban density. Third is the thermal comfort. Let us start with the urban form. The August results revealed that old urban configurations with high height to width aspect ratio and low sky view factor recorded the lowest daily air temperature averages, as shown in the third graph, by maximizing the shaded areas and minimize the exposure to solar radiation, while the new structured urban configurations with low height to width aspect ratio and high sky view factor recorded the highest daily air temperature averages, and also during the peak hours in August, due to the high exposure to the solar radiation. The traditional urban configurations with low and medium density have recorded the highest air temperatures during the early morning time and late evening, while recorded the lowest air temperature during the daytime and peak hours. It was noted also that all courtyards recorded the lowest air temperature at 3 p.m. as shown in the figures, despite their low wind speed. And the best street orientation was the streets oriented to the northwest and with less obstruction from buildings were windier than the others, and was found in Al Marija site. Regarding the April results, as shown in the first graph, during the midday hours, the traditional sites with high height to width ratio and the low sky view factor have recorded the lowest air temperature, while the highest air temperature during the daytime recording by the mid-density modern urban form. The results revealed that there is a significant correlation between the high height-width ratio and the air temperature, as the higher height-width ratio percentages, the lower the air temperature will be, despite the fact of the high urban density percentages. The results revealed as well that the highest wind speed was found in Al Fahidi and Al Safa 1 areas, which are high density areas near the mid-rise blocks and on the periphery urban blocks of the site, as shown in the figures. In December, the old urban areas as Al Marija and Sidro areas recorded the highest air temperature in the early morning evening time, and the whole day averages, as illustrated in the three graphs. While in December, there were slight differences in the results between the different simulated densities. Simulation results of Al-Marija area at 5 a.m. as illustrated recorded the highest air temperature while Jumeirah area recorded the lowest air temperature. Coming to the results of the urban density, we can conclude that in August and April, the average daily temperature or the peak hours temperatures are increasing by the increase of the urban density in both categories, except for the modern high density urban form, as could be noticed in the graph. All traditional urban forms recorded lower air temperatures than the new settlements with different densities during daytime in August, knowing that all the traditional urban forms have higher densities in comparison to the new urban forms with the same classification. Coming to Al Safa 1 area, which represents the high density modern form, recorded lower air temperature values than the modern sites with low and medium density, and this could occur due to several factors, such as the use of the attached villas, which reduce the amount of the exposed surfaces to solar radiation and the heat released by the blocks. The high height to width ratio, which provides more shaded areas. The low sky view factor value, which results in a decrease in temperature, and the wind corridors between the rows of the attached villas enhance the wind movement, reduce the air temperature, and enhance the thermal comfort. The high height to width ratio and the low sky view factor have a more significant impact on reducing the air temperature, increase the shaded areas, and enhance the thermal comfort despite the effect of the high urban density. And these are some images for Al Safa 1 area. The last part of our results related to the human thermal comfort. Various factors have an impact on human thermal comfort as following: environmental factors and psychological factors. The environmental factors refer to the air temperature, air velocity, mean radiant temperature, and relative humidity, while the psychological factors as the body metabolic rate, personal activity, age, and type of clothing. The thermal comfort in the PMV tool has a range of -4 to +4, the closest to zero, the optimum in terms of human thermal comfort. There is a correlation found between the sky view factor, height to width ratio, and mean radiant temperature on one side and the PMV levels on the other side. Due to the impact of the shading on mean radiant temperature values, which decreased significantly with the decrease of the solar radiation in the urban form with high height to width ratio and the low sky view factor. Consequently, the optimum PMV values were constantly noticed in these urban forms, such as Al Fahidi area followed by Al Safa area in August, as shown in the graph. The traditional urban form as Al Fahidi area with high height to width ratio, narrow canyons, low sky view factor, and low mean radiant temperature values, even though it is high density ratio, is more thermally comfortable compared to the open urban canyons with less urban density in the urban new forms. And these are some images for Al Fahidi area. At the end, we can conclude that the outcome of this study shows that the compact traditional urban forms enhance the thermal conditions in the hot dry regions, regardless of the density ratio, since the results revealed that the highest density traditional urban form achieved the optimum thermal comfort values due to the street geometries and the less exposure to solar radiation compared with the other types. By compromising and taking advantages of each urban form feature, the urban designers can reach an urban type that behaves the optimum through the year. Due to the rapid expansion, urban growth, and corresponding to the increase of the intensity, the urban heat island intensity could be optimized and mitigated by several strategies, such as the distribution layouts of the urban blocks, using the suitable building form and orientation, utilize the prevailing wind, height to width ratio, and low sky view factor. All of these will help in mitigating the urban heat island effect. Thank you very much for your attention, and I hope you have enjoyed this presentation. Thank you.